In a few years, a spacecraft may do something that looks like a mistake, aim itself straight at the sun, fall toward it on purpose, and skim past close enough to nearly cook itself, all so it can finally reach somewhere nobody has gone. Not farther out into the dark, up. Because there's a region directly above and below the sun's poles that, despite everything we've managed to explore, has almost never been seen. And distance isn't the reason. In raw miles, it's closer than Mars ever gets. What's kept us out is direction, and fixing that means deliberately diving toward the sun before a spacecraft can ever climb away from it. Here's the part that's easy to forget. You're moving right now, and fast. Earth carries everything on it. You, this video, every rocket ever launched, sideways around the sun at close to 30 kilometers a second, something like 67,000 miles an hour, all the time, whether you feel it or not. For almost any space mission, that sideways speed is free help. Aim for Mars, and a spacecraft is already moving in roughly the right direction at roughly the right speed. It just needs a nudge, a few kilometers per second of its own delta V, engineers' shorthand for the velocity change a spacecraft has to produce using its own engines to slot into a transfer orbit. That's why reaching Mars costs something like 4 kilometers per second. Try to go straight up instead, perpendicular to every planet's orbit toward the sun's poles, and that same 30 kilometers per second of sideways motion turns from a gift into a wall. A spacecraft can't just add thrust in a new direction. It first has to cancel out nearly all the sideways speed it was born with, and only then start climbing. Add the two together, and you're looking at something like 30 kilometers per second of delta V, roughly 7 times the cost of a Mars mission. That's the entire reason this is hard, and it produces one of the stranger facts in spaceflight. Reaching Pluto, billions of miles away, has taken less energy than parking a spacecraft above the sun's pole. The obstacle was never distance. It's always been direction.
Because that vertical trip is so expensive, only 2 missions in history have managed a real look upward. The first was Ulysses, a joint NASA and ESA spacecraft launched in October 1990. Instead of fighting Earth's sideways motion head-on, mission planners cheated. They sent Ulysses out to Jupiter first, let the giant planet's gravity bend its path nearly 80 degrees out of the plane of the planets, then let it fall back toward the sun on that steep new trajectory. It worked. Ulysses became the only spacecraft to fly over both solar poles, spending nearly 2 decades gathering the first direct measurements of solar wind pouring out of the poles at hundreds of kilometers per second. What it never delivered was a picture. Ulysses carried instruments for particles and magnetic fields, not cameras, so all of that history came back as data, never as an image. The second attempt is happening right now, and it's already made history. Solar Orbiter, launched by ESA with NASA in February 2020, has spent years using repeated flybys of Venus to tilt its orbit a few degrees at a time out of the ecliptic plane. By February and March of 2025, that tilt reached 15, then 17 degrees. Enough, for the first time ever, to look down on the sun's poles instead of across at its equator. The images ESA released that June show a pole in magnetic chaos. Patches of opposite polarity scattered across the surface, nothing like the tidy single pole of a bar magnet. ESA has described the ongoing campaign as a stairway to heaven. Solar Orbiter's tilt will keep growing to 24 degrees by 2026 and 33 by 2029, each step revealing more of a region that was, until last year, completely unphotographed. Even 33 degrees isn't vertical. It's a glimpse, not a flyover, and for anything closer to a straight overhead view, we'd need a mission neither of these was ever built to be. There's a second reason the vertical view matters, and it has nothing to do with the sun's surface. It's about the bubble we all happen to live inside. The solar wind, the sun's constant outward stream of charged particles, carves a cavity into interstellar space called the heliosphere. Every planet, every comet, every spacecraft we've ever flown sits inside it. Step outside and you're in the raw galaxy. A thin bath of cosmic rays and interstellar particles the heliosphere mostly keeps at bay.
For decades, the standard picture was a comet, a rounded nose facing the direction we're flying through the galaxy, a long tail trailing behind, more or less how it's still drawn in most diagrams. That picture came from limited data and reasonable guesswork. Nobody had a way to actually check it. In 2015, Boston University astrophysicist Merav Ofer and her collaborators tried a different kind of model, one that treated the hot and cold components of the solar wind as separate fluids instead of blending them together, and got a strikingly different shape. Not a long tail, but something closer to a croissant, folded and compact. A follow-up study on the cover of Nature Astronomy in 2020 sharpened the picture further. A central bulge with two shorter jets peeling away and no long tail at all. Ofer's team, now backed by a NASA-funded research center built specifically around this question, has kept refining the model since. It's still a model though, not a photograph. The Voyager probes crossed the edge of the heliosphere in 2012 and 2018, but even they never got far from the plane of the planets. Voyager 1 crossed roughly 35 degrees above it, Voyager 2 about 48 degrees below. Real angles, but nowhere near looking straight down. NASA's newest tool, IMAP, launched in September 2025 and has been mapping the heliosphere's boundary from a stable point near Earth since its primary mission began in February 2026. A serious upgrade in resolution, but still a view from inside the bubble, not from above it. To actually confirm the croissant, or the deflated version of it, or something nobody has modeled yet, someone eventually has to fly up and look back down at the whole structure from outside the plane. That flight has never happened.
So how would anyone actually close a 30 kilometers per second gap? Not with a bigger rocket. No reasonable fuel tank covers that. The answer mission designers keep returning to sounds backwards. To climb, dive first. It's called the Oberth maneuver, after German physicist Hermann Oberth, who worked out the principle in 1929. A rocket's burn is dramatically more effective at high speed, deep inside a gravity well, than it is far from anything, moving slowly. So instead of firing engines to fight upward from Earth orbit, a spacecraft lets the sun's gravity pull it inward first, accelerating harder and harder as it nears perihelion, its closest point to the sun. We already know how fast that fall can get. In December 2024, NASA's Parker Solar Probe hit 192 kilometers per second at its closest pass, the fastest any human-made object has ever traveled. Fast enough to cross the US coast to coast in about 20 seconds. Fire an engine right at that moment, at that speed, and the same fuel delivers far more added energy than it ever could in open space. The plunge itself supplies the push an engine alone could never provide. Solar sails offer a second route, slower but propellant-free. Instead of an engine, a large reflective sheet uses the gentle push of sunlight to tilt a spacecraft's orbit over months or years. This isn't purely theoretical. NASA's ACS-3 demonstrator unfurled an 80 square meter sail in orbit in 2024 to test lightweight composite booms that could scale up to sails 25 times larger. More ambitious proposals go further still. The Solar Polar Imager concept calls for a sail near 28,800 square meters, roughly 4 soccer fields, to drag a spacecraft up to a 75-degree solar orbit, a design serious enough to be endorsed in a national heliophysics research roadmap. Increasingly, mission designers talk about combining both moves. Sail inward first, fire an Oberth burn at closest approach to snap the trajectory upright, then keep riding sunlight out toward the poles. It's the layered, patient kind of engineering it takes to beat a problem no single rocket burn can solve. Say one of these missions finally makes the climb. What's actually waiting up there? For one thing, the sky gets cleaner. Every planet, Earth included, orbits through a faint haze of dust shed by comets and asteroid collisions over billions of years. The same dust responsible for the zodiacal light, that soft pyramid of glow sometimes visible reaching up from the horizon after sunset, far from city lights. A spacecraft climbing out of the ecliptic plane would rise out of that haze within months, into a darker, cleaner sky better suited to instruments hunting for faint signals.
whether that's light from a distant exoplanet or the faint structure of the cosmic microwave background, both routinely buried in scattered light from inside the disk. The solar wind changes too. Near the equator, it's slow and turbulent, drifting outward around 400 kilometers per second. Over the poles, where Ulysses and now Solar Orbiter have gotten glimpses, it's faster and steadier, 700 to 800 kilometers per second, flowing out through coronal holes in thinner, smoother streams. A spacecraft riding that stream would sit in a genuinely different radiation environment than anything flying through the ecliptic today. And then there's the view nobody has ever had at all. Looking straight down at our own solar system, the planets laid out as the flat disk they actually are, dust glowing faintly along that plane, the heliosphere wrapped around all of it in whatever shape it turns out to really have. We've photographed the surface of Pluto, we've flown through the tail of a comet, we have never once looked down at the neighborhood we live in, and that single missing photograph is what's waiting on the other side of a 30-kilometer-per-second wall for whichever mission finally decides to fall toward the sun before it climbs away from it. If you were designing that mission, what would you trust more? Years of sunlight nudging a sail into position, or one perfectly timed burn at the fastest, hottest moment of the whole trip? Let me know in the comments.